Hi guys, how's the technology today? Can you hear me?
I can hear you.
Good, thank you. So it's Wednesday, October 7th. We are talking about enzymes. It's our second lecture on enzymes. And we will have one more on Monday. And so if you don't have any general questions, let's get straight to the material. We have a lot to cover. All right, so can you see my slides?
Yes.
All right. So we talked about binding sites on the enzymes. We talked about substrates, binding sites. And it's all very well that the enzymes are so specific that they can select between different substrates. But that's not all, right? So their main function is actually to catalyze the reaction. The fact that they select a substrate is good. But once they have selected a substrate, they have to carry out the reaction. And if there's no reaction or the reaction is slow, then the fact that they selected a good substrate is inconsequential. So we don't really need that. We want an enzyme that can do the reaction. And so a chemist, Linus Pauling, I mentioned this name before, one of the most legendary chemists who made a lot of discoveries, and especially in the area of intermolecular interaction, hydrogen bonding. He won 2 Nobel Prizes. So he basically proposed that the enzymes, it's good that they bind the enzymes bind the substrates, but it's even better if they bind transition states of the reaction. So remember, transition states it's just a hypothesis, right? So we know transition states exist. The half-life or they live for what's the word? Yeah, the half-life of a transition state is shorter than that of a single molecular vibration, right? So nobody has ever been able to observe a transition state. Nobody has ever been able to take a picture of a transition state. So it's just a hypothesis. So we can only hypothesize what it looks like, right? And so what he says that is actually, so this hypothetical transition state. So if you can imagine what it looks like, so the enzyme has to bind it strongly. And if it binds it strongly, obviously it decreases its energy, right? So if something is bound, that means the energy goes down. And so he proposed that that's what the enzymes have to do. And they have to bind these transition states better than substrates. And that will lower the activation barrier. So let's look at some specific example. So let's say we have a stick. We have some kind of enzyme. Let's call it stickase or something. All right. So stick is it's a substrate, and ace, we're going to break it, stickase. So let's say we have this metal stick that we're going to break in half, right? And the enzyme is going to accomplish that. And so the transition state to break this stick looks something like this, right? So when the stick is bent, but it's not broken yet, it's half broken, right? So you can see that this surface here is starting to go, right? Starting to break. Eventually, when it's broken, the 2 pieces are produced. And you can see that this is just a normal reaction energy diagram. When you have the full stick, when you have the products, 2 half sticks, and there's a single transition state, right? So this will be an uncatalyzed reaction. So let's say our enzyme binds the substrate very well, okay? So the binding site or the active site is complementary to the stick. So it binds it very strongly. It will not bind any other kind of shape, right? But this will slow down the reaction. You can look at the energy diagram. So here's the substrate, the enzyme comes in, binds the stick, the energy drops because of the binding, and then now look, it has to climb all the way up there to break the stick. Why? Because the enzyme cannot accommodate for the transition state to break the stick, right? So the bent stick cannot be accommodated by the enzyme. And that's why the activation energy is so large. You can see here, it's given by this delta G of the transition state of the catalyzed reaction. And you can see for the uncatalyzed, it's even actually better, right? So it's better actually for this reaction to be uncatalyzed than catalyzed. And so what needs to be done, you have to have an enzyme where basically there is a binding site which can accommodate the stick, but there's even better binding site which can accommodate the bent stick, right? So you can see the stick will fit in here, but then there is this extra pocket which will allow for the stick to bend and protrude, or basically occupy the space in the enzyme where basically the magnet will draw the stick towards it, right? And the magnet will create this shape. And then the stick will break. So you can see here, so the original event is the substrate will bind to the enzyme with a small activation energy to give you the enzyme substrate complex. And the energy of the enzyme substrate complex is not so much difference of the energy of the substrate. So in other words, the stick is occupying this site, but it's happy, partially happy, because the interaction is very small. The interaction is on this side, and the interaction is on that side. Not too much of the interaction, right? So the energy is not so much different from the energy of the substrate. But then the activation energy to break it is much, much smaller. You can see here delta G of the transition state is significantly smaller than delta G of the uncatalyzed reaction, right? So this is the key for enzyme function. So the enzymes have to bind transition states better than the bind substrates, right? But again, the challenge here is that we don't really know what transition states look like. So this is something that we have to hypothesize. And when you design an inhibitor of an enzyme, obviously you want to design an inhibitor that looks like transition state, not like the substrate, right? Anybody remembers from organic chemistry the name of this postulate? Hammond postulate? Actually, it's a general chemistry, not even organic chemistry. It's just mentioned in organic chemistry, but it originally, you guys learned it in general chemistry. Anybody remembers what this means? No? So, well, look it up. I'll just tell you, but put it in your notes that basically species which are close in energy, they also close in structure. Okay, so very useful Hammond's postulate. So if you don't know what the transition state looks like, compare basically the energies. If the energies are similar, then likely the structures will be similar. So Hammond's postulate, very useful. All right, and the basic catalytic mechanisms. So the enzymes may use one or a combination of the following. So we have acid-base catalysis, right? So here, you know that the reactions can be catalyzed by proton shifts, right? The protons can move from one part of the molecule to another. They can come in, they can leave. covalent catalysis and metal ion catalysis. So let's look at an example of each. So for example, here we see that there's an amide bond. It's going to be hydrolyzed to give, it's going to actually be converted to an ester to release the free amine and an ester at the end, right? So in this reaction, remember from the carboxylic acid derivatives chemistry, right? When you have tetrahedral intermediates, so the alcohol of the lone pair on the hydroxyl group will attack the carbonyl of the amide to form this tetrahedral intermediate. But then you have this proton sitting on the oxygen, right? So it's very easy for the reaction to go back to regenerate this alcohol until this proton jumps from the oxygen onto the nitrogen. How can it jump? Now, don't worry about these additional details. What I want you to take from this slide is the idea that there are different ways for this. So for example, this reaction can be uncatalyzed. For example, water can pick up a proton here and can deliver it to this nitrogen, right? And this reaction will be uncatalyzed. Or this base can be part of an enzyme and then can protonate this nitrogen, and the base will deprotonate this oxygen to give us this intermediate. And when these electrons come back, like so, nitrogen will leave, right? To give us the free amine and the ester. So here you can see that the catalysis is based on the proton transfer, right? So if there's no proton transfer, the reaction will simply go back. And this proton transfer will expedite the forward reaction. So this is acid-base catalysis. And what kind of amino acids? So you already know from 20 amino acids, you know, carboxylic acids, glutamate, aspartate, that they have protons that can participate in such reactions. So these will protonate the substrate. Their conjugate bases will deprotonate the substrates. Lysine, arginine. So here you have protonated nitrogen. So this will protonate the substrate. This will deprotonate the substrate. Cysteine. Now imidazole of histidine. Again, in this acid form, it will protonate. In the base form, it will deprotonate. Alcohol of the serine. So all of these, and tyrosine. So all of these can participate in the acid-base chemistry at the active site of the enzymes, right? So that's one way the enzymes will accelerate the reactions by protonation, deprotonation required in the mechanism. Another is covalent catalysis. So here, let's say, here we need to break the AB bond. So basically it's hydrolysis, right? We're gonna break it into A and B. Now the reaction with water is slow. Reaction with water is slow, but let's say you have a catalyst, you have an enzyme, and the reaction takes a different path. So it changes the reaction pathway. So here, because the original reaction is slow, the nucleophile on the enzyme can come in and attack the A, and B can leave, right? So we form a new species, AX, and B is the leaving group. But then the AX in the second step will undergo cleavage with water to generate A, B, and regenerate the catalyst, X. So even though these are two steps, so this is one step, right? One step, but it's slow. Now this is two steps. But they're fast. right? So overall, the reaction is faster with the catalyst, and this will usually require a nucleophile on the enzyme. So here you have serine, thiolate. Remember, this is part of amino acid cysteine, amine, lysine, or carboxylate, aspartate. All right, makes sense? Any questions about this? So covalent catalysis, we'll see actually examples of covalent catalysis when we talk about chymotrypsin and lysozyme later in this chapter. There will be examples of covalent catalysis. Even though it involves multiple steps, but each step is significantly faster than the one step in an uncatalyzed reaction, which is slow. And finally, many enzymes utilize metal cofactors. So remember, metals are what? They are Lewis acids. Lewis acids, they love electrons. Remember Lewis acid? It's a species which attracts electrons, electron pairs, right? And so the metals will interact with negatively charged sites on the substrate and stabilize them, right? If they stabilize negative charges, they bring down the energy of the transition states. That's one way. And secondly, they participate in oxidation reactions. For example, one of the most common oxidation reaction in biological media is oxidation of iron 2+ to iron 3+ and back. Right? A very common reaction in biology. All right, any questions about anything we've talked about so far? So we looked at how the enzymes work. We'll look at the reaction energy diagrams, how they accelerate reactions, the mechanisms. Any questions so far? So if you do have questions, once you read the book, please put this in the discussion section and we will analyze that in more detail. All right. So now we're going to talk about enzyme kinetics. Remember, for a reaction to be successful, there are two terms. There's kinetics and there's thermodynamics. So thermodynamics talks about energies, right? So the reaction proceeds spontaneously if the delta G of the reaction is negative and the overall energy is decreasing and the reaction is exergonic, right? Kinetics talks about the rate of the reaction. Remember the bag of sugar, right? So even though thermodynamically sugar will burn very rapidly, provided there are some catalysts, but if there is no catalyst, because of poor kinetics, the bag of sugar will sit on a shelf and nothing will happen to it. So for the reaction to be successful, you have to have kinetics and thermodynamics in your favor. And so the rate of the enzymatic reaction will be affected obviously by the enzyme, right? The enzyme, the substrate, various effectors. So we talked about allosteric regulation, right? And temperature. Obviously at high temperature, the reactions are faster. So we'll talk about the kinetics, the theory which has been developed primarily by two scientists, Michaelis and Menten. And that's why this type of kinetics is often referred to as Michaelis-Menten enzyme kinetics. So, so why study enzyme kinetics? So the primary goal is basically quantitative description of biocatalysis. So far, we've been talking about, how different attractive interactions, how stabilization transition state works, how the substrate binds, how the enzymes are inhibited if the structures of the inhibitor are similar to the structure of the substrate. But we have not been able to quantitatively express those, right? So for example, if I give you two inhibitors, you may say this inhibitor is better than that, but why, right? What kind of quantitative description can you give me that shows that this inhibitor is better to use than that inhibitor, right? So why, for example, when you take a medication, right, if you have two different choices, this medication over that medication, why do you need to take 200 milligrams of one and 2 milligrams of the other to achieve the same effect, right? If the inhibitors work with the same mechanism, they're just different compounds. Why you have to use 100 times more of one than the other, right? So that comes down to kinetics. Comes down to kinetics and comes down to quantitative description of the two, of the interaction between the inhibitors and the enzyme. So we'll talk about the order of binding of the substrates. If there are more than one substrate, we'll talk about acid-base catalysis. That's also part of the kinetics. Kinetics will help us understand the catalytic mechanism, right? So specifically how so far we've talked about mechanism in general, but kinetics will actually allow us to validate these proposals, right? So any mechanism has to be consistent with the kinetics. You remember from organic chemistry when we use kinetics to validate a particular mechanism? Can you think of such mechanisms? It was in Ochem 1. So we use the kinetics to validate what kind of mechanisms? Come on, guys. What am I drawing here? Participate. What does this mean?
There's substitution reaction.
Yeah, so remember how we use kinetics to tell which one is which? Remember how the concentration of the nucleophile, does it play a role in the SN1 or SN2? You forgot the SN1, SN2 reactions? Remember in SN1 reaction, the leaving group leaves first in a rate determining step. So the concentration of nucleophile, does it matter? Well, we need to look this up, guys, because so this what we're going to talk about is kind of based on our understanding of kinetics from general chemistry, from organic chemistry, right? So some of the basic kinetic expressions. So what we're going to talk about today, if stuff is not clear, please go back to your general chemistry book. All right, so I'm going to add a slide, new slide. I'm going to add a slide. And first I'm gonna, obviously kinetics is gonna be the measurement of reaction rate. So the question is, what kind of rate are we gonna measure? The problem is that the reaction rate will change as the reaction proceeds, right? So if you think about it, so the rate law will include the concentration of the substrate, right? So the substrate is going to be undergoing the reaction, and you start with a lot of substrate and you end up with very little substrate. Most of it will be converted to product. So reaction rate will be higher at the beginning of the reaction, right? When the substrate concentration is high, and it will be lower at the end of the reaction when it is low. So we're going to talk about what's known as initial rate or initial velocity. Initial velocity. So, or initial rate. Where we're going to use original substrate concentration. Just think about it. The substrate concentration is always so much higher than the enzyme concentration, right? I mean, that's the whole point of the catalyst, right? So you use catalysts in very small quantities. And so the concentration of the substrate can be 1,000,000 times higher than that of the enzyme. And so at the beginning of the reaction, obviously, the enzyme can only convert so much substrate into the product. And so if we measure this initial velocity, then the substrate concentration will change very little, right? And we can use the original number for the substrate concentration. So for example, if we say the substrate concentration is 1 micromolar, then after a few seconds of the reaction, we can still say it's still 1 micromolar, even though it's 1 micromolar minus 0.0003 micromolar, right? So initial velocity will allow us to use the original substrate concentration. And so the expression that we're going to use to derive the rate law will be the following. So we have the enzyme reacted with the substrate with the reaction constant K1 giving us enzyme substrate complex, and this can go back K -1. Oops, I need some space. This can go back. The complex can form, and the complex can fall apart. K -1. And then once the enzyme substrate complex is formed, then the reaction can occur with some kind of rate constant K2 to give the enzyme and the product. Okay. So based on this expression, we can express the initial velocity as V naught reaction rate constant K2 times enzyme substrate concentration, right? So it's the enzyme substrate converting into the product with the reaction rate K2. So this is our starting point. This is our starting point. Now, the main question is, all right, so how do we know what this enzyme substrate concentration, enzyme substrate complex concentration is? Okay, so we need a way to express this using parameters which are known or can be obtained by experiment. And here is our main assumption. It's known as a steady state sometimes called approximation, sometimes it's called assumption, which will allow us to derive the expression for the enzyme substrate complex. Basically, we say that the concentration of the enzyme substrate complex during the reaction is always the same. So in other words, you can see here it's forming as the enzyme and the substrate coming together to form it, and it's breaking down to form the enzyme and product. And as the reaction proceeds, our assumption is that its concentration always stays the same. So in other words, the amount produced always equals the amount broken down. Okay, so that's the assumption. And so based on this assumption, let's try to derive the expression for it. So rate of ES formation so it's formed by the through the rate constant K1 and the enzyme has to encounter the substrate. And one thing we can you can ask, okay, what's the enzyme concentration at any given point? We don't really know, right? So because some of it will be bound to the substrate, right? Even in the initial time when the reaction just started, quite a bit of the enzyme will already be complexed with the substrate. And so we can express it as follows. So K1 so this will be enzyme total minus, so enzyme total minus the amount of the enzyme that has been complexed with the substrate. Does this make sense? So this will equal the amount of the enzyme which is free, right? Subtract the amount of the enzyme which is complex with the substrate from the total amount of the enzyme, and that will give you the free enzyme. And that will be times substrate. So this is the rate of the ES formation. Rate of ES breakdown. rate of the ES breakdown. So let's look at the ES. So one way it can break down is to go back to regenerate the original enzyme and substrate, right? This will be through the reaction constant K-1 times the concentration of the enzyme substrate complex. And the other way it can break down, if the reaction occurs, this will be through the reaction constant K2 and the concentration of the enzyme substrate complex. And so the steady state assumption tells us that the formation, the rate of the formation equals the rate of the breakdown. And so that we take the rate of the formation, which is, which is this parameter. So K1 enzyme total minus enzyme bound to the substrate times the initial substrate. And we're going to equate this to the rate of the breakdown, which is this parameter here. This makes sense so far? No, doesn't make much sense. Any questions? Anybody? All right. So remember, what we are after is this enzyme substrate complex, right? We need to know its concentration to be able to derive the rate expression. So we're going to solve this expression for the enzyme substrate complex. Now there's a lot of algebraic transformations. I'll refer you to page 200 in the textbook. You can look at how algebra was used to actually transform this expression into this one, where it was solved for the enzyme substrate complex concentration. And this will be the enzyme total. Times substrate over substrate. And then we'll have a term which contains all three rate constants. K-1 plus K2 over K1. Now, so we have a term with three rate constants. So obviously those don't change. And we can actually combine them all together. And introduce a new constant, which is combination of all three. And it's known as Michaelis constant. Michaelis constant equals k negative 1 plus k2 over k1. Michaelis constant. All right. So now that we have the expression for the enzyme substrate concentration, enzyme substrate complex concentration, now we can plug it into this equation. And so V naught will equal K2 enzyme total substrate Km plus substrate. Okay, so we can simplify this a bit further. Okay, so let me actually go create another page. Want to keep, yeah, let me keep this. Insert new slide. Insert new slide. So I'm just gonna rewrite this. Okay, one thing to keep in mind here is that when you, because there's only a certain amount of the enzyme present in the reaction mixture, as you increase the concentration, obviously the initial rate will go up. It will go up, but it will not continue going up indefinitely. At some point, it will reach a point of saturation. Like so. Point of saturation. And why is that so? As basically when you occupy all the binding sites on the enzyme. So in other words, the enzyme is fully saturated. And then you add more substrate and nothing happens anymore. The enzyme is full. Yeah, all the seats are taken. It cannot take any more substrate. And then there doesn't matter how much more substrate you add, there will be no more seats available. The rate reaches maximum. This is known as Vmax. Vmax, and usually Vmax is observed. Vmax Zmax is observed when the enzyme substrate concentration equals enzyme total, right? So all the enzyme is converted into enzyme substrate. No more free enzyme. No more free enzyme. And when this happens, then we can substitute here that we can say that Vmax is achieved when the enzyme substrate concentration equals the enzyme total. So we put the Vmax here. Vmax, concentration of the substrate, Michaelis constant, plus the concentration of the substrate. All right, so finally we achieved the expression we were aiming for. So this is known as Michaelis-Menten equation. Michaelis-Menten equation. Okay. And so basically what this allows you to do is, so look, basically you know all the parameters, right? So you know the initial velocity, you can measure the initial velocity as you change the substrate concentration. So the question is, how do we determine the Vmax and Km? Okay, Vmax and Km. So these are very important parameters in the enzymatic function, Vmax and Km. So Km can be characterized, let's say, let's say V naught is somewhere here. Basically one half of the Vmax. Okay. So say V naught is one half of the Vmax, then we have Vmax over 2 on the left, right here, Vmax over 2 equaling Vmax times the substrate concentration over Km plus substrate concentration. So we divide by Vmax both sides, basically simple algebraic transformation, and we come up with Km, Km equaling substrate concentration. So the interpretation of the Km that we should remember, Km is the substrate concentration at which the reaction rate is half maximal. Should write this down. I'm not going to write this down since I write pretty slowly, but write this down. So Km, so Michaelis constant, is the substrate concentration at which the reaction rate is half maximal. Okay, and it's right there. It's right there. So another way to understand the Km, it can also be defined as also can be defined as dissociation constant. Dissociation of the substrate from the enzyme. Let's look at this. So we had this expression for Km. Km was equal K2 plus K negative 1 over K1. So when a reaction is slow, when K2 is limiting, when K2 is limiting, Km, so we can basically take this out of the reaction of the formula and leave the K negative 1 over K1, right? Basically, and this is the ratio of the reverse reaction over forward reaction, and that's the same as dissociation constant. Okay, so then the Km is the measure Km is the measure of affinity. Of substrate to enzyme. Does it make sense? Yeah. So Km basically, so one way to look at it. So there's a definition, obviously. You can express it in terms of 3 rate constants, but probably the two best ways to understand Michaelis constant is as a substrate concentration at which the reaction rate is half maximal, right? So in other words, you want the Km to be small. So when the enzyme has a small Km, that usually means that you need very little substrate to achieve very high reaction rate, right? And secondly, it also tells us about the measure. It's a measure of affinity. So if the Km is small, and in most cases reaction rate is rate limiting, right? So the first So these two equilibrium constants, right? The substrate comes in, goes, comes in, goes. So these are all very high numbers. K2 is slow. K2 is small. Reaction rates are much smaller than the rates for the binding events, because binding doesn't involve any breaking of the bonds, right? And so the rates for binding are much higher than the rates for reactions. And so in most cases, K2 will be much smaller than K-1 and K1. And so in this case, it's going to be a measure of affinity of substrate to the enzyme. So if you have a Km in the nanomolar region, for example, then you can say that, yes, my substrate binds to the enzyme very strongly. Does this make sense? Okay, so the question is, how do you calculate these? How do you calculate these? And actually, quite simply, there is a very easy way to do that. And you will have to do that a couple of times in sapling homework. Sapling homework. So again, let me redraw this. Let me redraw the Michaelis-Menten equation. So V naught equals V max substrate, Michaelis constant plus substrate. So we're going to use what's known as a Lineweaver-Burke plot. A Lineweaver-Burke or equation. So what we're going to do, we're going to take double reciprocal of this. So the left-hand side, we're going to put V naught in a denominator. And on the right-hand side, we're going to switch to numerator and denominator as well. Km plus substrate concentration. V max times substrate concentration equals. So we're gonna divide each of these terms in the numerator by the denominator. So this will be Km over V max times 1 over substrate concentration plus 1 over V max. And so this is, if you think about it, what this is the slope equation for the slope, right? How does it go? Y equals mx. Is this right? Mx.
Yep, y equals mx plus b.
mx plus b. Okay. Yeah, I've never taken a math class in this country, so I don't know which particular letters are used for the equation for the slope. So this will be y, right? Km over V max will be the m. Reciprocal concentration will be x. And the reciprocal V max will be b. And so when we do the experimental measurements, so on the y-axis, we will have the reciprocal initial velocity. On the x-axis, we will have the reciprocal substrate concentration. And we're gonna get a straight line, right? Whose slope is, what's the slope?
The Km over Vmax.
Km over Vmax. Now this is a little harder. What's the y-intercept?
One over Vmax.
Perfect. Perfect. 1 over Vmax. And what's the x-intercept? Now this is a little harder. It give you a hint, it's negative. Yes.
Is it just negative Km?
Well, it's reciprocal Km, yeah.
Gotcha.
All right. Yeah, in fact, actually, this Lineweaver-Burke plot actually gives you more points than actually you need to, because you can see it gives you actually two intercepts and a slope, and you're only looking for two parameters, right? Vmax and Km. So for each enzyme, you can derive Vmax and Km, and then compare them, for example, compare different Km values and Vmax values, and obviously for different substrates, you can use them, and so on and so forth. So, and we're gonna use them for inhibition. Now, so far, are there any questions? So Lineweaver-Burke equation. So on Saplin, you're probably going to be given a couple numbers for velocity, couple numbers for substrate, and you're going to have to take the reciprocal and build a slope and calculate the Km and Vmax. All right, so there are some slides here which kind of describe what we just talked about. There's just some summaries. You can look at those in more detail. What I would like to do is actually, yeah, so because you can see 1/2 Vmax Km. So basically this is all we've talked about. Lineweaver, this is Lineweaver-Burke plot. Double reciprocal. So what I want to talk about is this Kcat over Km. Let me actually have another slide here. So in general, so what we talked so far about was a simplified expression for how enzymes work. In general, however, the enzymes may have more complex mechanisms. So for example, the enzyme can come in and react with the substrate. Here you have a K1, K -1. This will form the enzyme substrate complex. Now this can proceed forward, but it can also go in reverse direction, which we haven't talked about. K -2. And this will give you enzyme product complex. And I told you last time that doesn't necessarily mean that the product will be so eager to dissociate right away. It's possible it'll sit there for a while, and the rate limiting step is actually K3. Right? So all these steps before that happens fast, but the product just sits there, blocks the active site, and doesn't allow more of the substrate to come in which case the K3 will be the rate limiting step. In that case, so let's say if K3 is rate limiting step is, remember RDS, I will not decipher it for you, you should know that, is RDS, rate determining step. Then the reaction rate, the Vmax, will be totally dependent on this K3 constant. K3 times enzyme total. Times enzyme total. And so K3 in this case, so because any of these rate constants can be part of the rate determining step, so a new rate constant is introduced. It's going to be general rate constant. General rate constant. General rate constant, and it's going to be K cat. K cat. So in this case, K cat will equal K3, but it doesn't have to be. So K cat is often called the K cat, often referred to as turnover number. Turnover number. Basically, it tells us it's a number of substrate molecules which are converted to product substrate molecules converted to product in a unit of time. So obviously the faster the kcat, the higher the kcat, the more efficient is the enzyme. But the enzyme efficiency in general is determined by a slightly larger term. And so let's look at that. So let's say V0, V0 equals, so instead of K2, or we're gonna put Kcat, which is the general one, Kcat times enzyme total. Substrate concentration. Km plus substrate concentration. So in many cases, especially in a cell where the enzymes live, right? In a cell, substrate concentrations are usually pretty low, okay? Which, if you look at this expression here, if this is low, this can be canceled, right? And in which case, the expression that we have for V naught is Kcat over Km times enzyme total times substrate concentration. So this term hold on a second. So the ratio of Kcat over Km is a measure of catalytic efficiency of the enzymes. Or you can say kinetic efficiency. And let me give you some numbers. Let's say when Kcat, okay, let's put it like this. When Kcat over Km reach numbers as high as 10 to the 8th to 10 to the 9th. Now this is molar reverse molars, reverse seconds. Then we say that the enzymes achieved catalytic proficiency. Hold on a second. The enzymes achieved catalytic perfection. Catalytic perfection. So the question for you, why is there such a thing as perfection? Why can't the enzyme improve even further? So in other words, we have the upper limit to as far as how efficient the enzymes can be, right? And it's this number, 10 to the 8 and 10 to the 9th. You can't have an enzyme, for example, with 10 to the 12th. No matter how, no matter if it keeps evolving for another thousands of years, it's going to be very hard to break this barrier of Kcat over Km equaling 10 to the 8, 10 to the 9th. So we say catalytic perfection. So can you think of a reason why the enzymes cannot be better? Well, it's a difficult question. And it has to do actually not with the enzymes themselves, just species in solution. So the substrate has to move around. And the substrate has to encounter the enzyme, right? So if the substrate doesn't encounter the enzyme, no matter how efficient the enzyme is, it will not catalyze the reaction, right? But the enzymes which have achieved the catalytic perfection, we always say that every time the substrate finds an enzyme in solution, basically hits the enzyme in solution, it undergoes a chemical transformation. And in this case, the enzymes have achieved catalytic perfection. So basically, we say that the catalytic efficiency of the enzymes is limited by diffusion, right? By diffusion. So, but the amazing thing is that, so we talk about these binding sites, right? So something that is still mind-boggling to me. So you have a large enzyme, right? Thousands of amino acids. There's one small binding site. So you would think that the substrate has to come not only close to the enzyme, but it has to come close to the binding site. It has to get inside, and then the reaction will occur. So what happens if the substrate hits the enzyme or bumps into the enzyme on the side opposite from the active site? What do you think will happen? The active site is on the opposite side, right? So it will just bounce at the enzyme and come off and be on its way. Well, it turns out that with the enzymes that have achieved catalytic perfection, it turns out that they will catalyze the reaction every time the substrate bounces into them, which is amazing. So even though the binding site could be far away, the enzymes find a way to lead the substrate toward the binding site. I mean, that's why the enzymes are so big, right? So they fully evolutionarily developed to basically to catalyze reactions even when the substrate is not close to the active site, right? The moment they feel the substrate is close, they find a way to bring the substrate into their active site. It's amazing. It's almost like the enzymes are living creatures who found a way to basically to grab the substrate with their hands and bring them to their active site.
Is that done by like a conformational change in the protein to like move the active site, or does it just like grab it and then pull it to the active site?
Yeah, so this is an active area of research. We know very little. I mean, that's why enzymology is such an exciting field, because we understand so little about it. Yeah, so it's some type of attractive interactions, right? So the attractive interactions on the surface of the enzyme somehow have to bind to the substrate, and it's almost like chemotaxis. Have you heard of the word chemotaxis? Is when when the substrate is led by the let's say by stronger interactions. Let's say the interactions are weaker, And then on the adjacent side, they'll be stronger. So the substrate will move over, keep moving over until the forces get stronger, stronger, stronger until it gets into the binding side. Yeah, something like that.
Cool.
All right, any other questions for today? So we've covered a lot of kinetics. Now there's obviously some pages to read for you. I can give them to you now if you're interested. So start with 198. And what we've covered today. Um, 2 or 3, so 5 pages. So if things are not clear, just read the text. If things are still not clear, write about them in the discussion on Canvas, and we'll tackle them all together. Sounds good? All right, well, I'll see you all on Monday. Stay safe and have a good weekend.
Thank you.
Bye.